in organic chemistry. Now, I hope you can see the slide. Let us begin it. So now we will understand the reactions involving substitution and addition reactions along with elimination reactions. Okay. So what exactly we can discuss today and tomorrow's classes is we try to make you aware of substitution reactions, addition reactions, and also elimination reactions. So many of you are already aware of substitution reactions. The name itself says you are substituting one atom in a molecule. Okay? So it is a class of chemical reactions where an atom or ion or a group of atoms or ions is replaced. Simple, because it's substitute by other atoms. So there are different classes. I am pretty sure that many of you are already aware of this, depending on the kinds of substitution, kind of atoms and groups. So one is nucleophilic substitution, where you have a nucleophile, like it's more like a donors. In Lewis basis terms, they are electron rich and they provide electron pair for bonding with substrate. Substrate means organic molecules. We can also have electrophilic substitution. Instead of a nucleophile, we have an electrophile, which is electron deficient. So the substituent is deficient compounds, where once it pairs a bonding, it forms a molecule and with free radicals. Of course, instead of nucleophile, electrophile, we can have free radicals which are involved in substrate binding. Yeah, so these are the three categories. I'm pretty sure that many of you have heard of first two very like many a times, these two things. So before we go into these parts, actually the main reason being in today's class and other topics is these topics what I'm going to discuss now you might have already read in your earlier classes, but some points I would like to elaborate, okay, which might be new for you, and other topics might be very obvious like SN1, SN2. So let us discuss slowly. So first you should be aware of the term nucleophile. It can be negatively charged or neutral ions where they donate a pair of electrons like bromide, alkyl groups and so on. And electrophiles, these are positively charged or neutral molecules which will accept a pair of electrons like any cations. So simple, take a nucleophile and bring it to an electrophile, it forms a bond. Okay, as simple as that. But you take a nucleophile and interact with electrophile, it forms a bond. Okay, either by transferring the electrons or keeping the lone pair of electrons towards the electrophile. Okay, so these are the ways by which the substitution or the bonding between nucleophile electrophile happens. Okay, so neutral and charged nucleophiles. All the time remember the charge balance is must. Just now, why we have shown A, B, nucleophile, electrophile. Let us come to organic molecules. So you already know that carbon can form 4 bonds, and whenever it is linked to an halogen or electronegative atom, the electrons will be more directed towards the electronegative atom, so it is delta minus, and carbon gets sliced positive charge. Okay. So what happens because of this electron withdrawing group? This sp3 hybridized tetrahedral carbon will undergo substitution or elimination. Okay. So for example, you have a system like this. Halogen is there and you have carbon center, same arrangement like this. You substitute X with Y. Okay. You remove the X, you get Y, and X minus will go off. Or you remove X and hydrogen together. This is called elimination. So you are breaking the hydrogen halogen bond. So you get hydro halide along with halide will be removed by means of a substituent what you can add. I mean the reactant what you are going to add. So this is elimination and other one is substitution. Let's discuss one by one. Okay, so as I told you, halides are very good leaving groups. They like to leave because it creates slight positive charge and then it moves away. So alkyl fluoride, chloride, bromide, they are all very good leaving groups. In this, bromides and iodides are the best leaving groups as compared to chlorides and fluorides, yeah? Because of bigger sizes of iodine and bromide. Now look at this reaction. I think many of you are familiar already by looking at this. You have a tertiary bromo compound or 1-bromo dimethyl ethane. If you have like this, when you bring water to this, okay, what happens? You get ethane is converted into ethanol. So bromo group is gone, OH is coming replaced, and HBr comes as a side product, byproduct. Now, if you look at this, if the reaction concentration of one is doubled, the rate of the reaction also means how quickly the reaction converts also increases, doubles. If the water concentration is increased, the rate does not double. Okay, so what does it mean? It means the rate is entirely dependent on the substrate, what substrate you are taking. Even if you take the reaction 1 ml of water, 1 liter of water, the impact is same. Only if you want to increase the reaction rate, change the substrate concentration of this. So that is the reason why it is called, you are substituting Br with OH, substitution, nucleophile you are using water molecule, and unimolecular because it is only dependent on the substrate, not on the medium. So it is substitution unimolecular nucleophilic reaction, SN1. So this is the best example you must have studied. The same thing I am going to show you other way. Probably in your earlier sections or classes you must have studied this. This tertiary butyl bromo compound, put water, you get this. Let's see. First one is you generate a carbocation because bromine will leave, okay, as bromide ion, and you get tertiary butyl carbocation. This carbocation is electron deficient. It likes nucleophile to attack. So water lone pair of electrons will bond with the carbocation. So you get an oxonium ion. And then you have the deprotonation, which is a fast process. Then you get tertiary butanol along with hydronium, like acidic water. Okay. So see this is the recombination. So water bonds with a carbon nucleophile, and then you get tertiary butanol. Okay, after the carbocation is formed. Okay, so this is a very, very standard example which many of you might have already studied. This is SN1 mechanism. Now let's go deeper into this. So first one is you have breaking up of C-bromo bonds and then addition of OH bonds. Okay, so nucleophile attack will be on the carbocation, and then proton rearrangement, then finally you get tertiary butanol. Okay, so the rate of bond breakage is slow, whereas the reaction and the proton dissociation is quick. Okay, so this is the general mechanism of SN1 reaction. And one important aspect which I think many of you might have already studied, or probably it must be a new addition. In SN1 reaction mechanisms, you can see here, this is the arrangement. Okay, so as you can see now, you have like this bromo compound here, and two groups are pointing towards me and one towards you. So this sp2 hybridase carbon atom can have multiple or different attacks. Nucleophile can come and attack in different ways after carbocation is formed. So bromine will leave, so you get carbocation. Water can react through this side or other side, like here. Okay. For example, you can see this one. Okay. So these are the two groups I'm talking about. So water can attack from here or from here. If you see that, if you see this, we can get an inverted configuration with respect to where you have started. Means bromo is here, the OH group will be in the inverted side, opposite side. This is one configuration. Or you can get OH in the same side. Wherever Br is there, you can get Br on the same configuration. So such kind of arrangement you can see in the case of SN1 reactions depending on where the nucleophile attacks. Now let's take an example. So you take a molecule like this, an SN enantiomer, okay, and you remove that chloro group, you generate a planar carbocation, and this you are reacting with iodo molecule. So chlorine is being replaced and iodo attacks. If it attacks from the left side, it attacks here. If it attacks from the right side, you get this. So you can get a enantiomers R or S depending on how the iodide molecule attacks after carbocation is formed. So this is very important. So what happens is you get R and S. So overall optical rotation will be 0 for this kind of reaction. Now, I think even this is a very familiar slide for many of you. So you have alkyl halide with only hydrogens like bromo, methane, and methyl bromomethane, and tertiary butyl. You see, for the tertiary butyl group, the rate of a reaction is enormous, very high. But if you take a bromomethane and you want it to go through SN1 reaction mechanism, it is very hard. Okay, because the carbocation is not formed here. Okay, it starts forming from here, but it is slightly like delta minus and so on. But here it is positive. Okay, so which gives rise to highest rate. Now, okay, so again, in this case, we can get SN2. Let us discuss slowly about that. So the better the carbocation formed, the better is the SN, like for example, the substitution happens accordingly. So compared to primary, secondary, tertiary group forms excellent stability of the carbocation. So the reactivity wise, tertiary groups are very good. Okay, why? Because we are breaking C halogen bonds and then we are allowing OH bonds to interact. So that is the reason more stable the carbocation is formed, the faster will be the reaction. So these are very like standard examples many of you are familiar with. Now let us come to a point. Many times I'm telling about water. Take water and put with tertiary butyl chloride, you will get tertiary butyl alcohol. What about solvent systems? If we take acetic acid, methanol, water, you are changing dielectric constant. You know that water is polar, so it has got high dielectric constant. Methanol is medium or what, low polar, 33, and acetic acid, you see the dielectric constant is even less, but you see the rate of reactivity. It's enormous for water, whereas these two it is because the tertiary carbocation, once it is formed, it likes to react with some nucleophile, and also the polarity of the medium also dictates the reactivity. So the polarity, which is dielectric constant, and how its ability to stabilize the intermediate, means once the carbocation is formed, how it stabilizes is also important. Okay. Now please see here, you have a bromo substituted product. This should be leaving and you get cyano group. So halogens in general are good leaving groups, and cyano group should be attached. So here it forms very fast if you do the reaction in water. But if you do in methanol, you see the rate of a reaction. It drops down drastically. Okay. So, and whenever you have dielectric constant below 15, you generally call it as non-polar solvents. Now, as I already told you, let us look in a pictorial representation of mechanisms. You know that we have a halo compounds, we are converting into nucleophiles like OH by substitution. So the x-axis shows reaction coordinate, reaction is converted into product, reactant, product. And energy, if you look at this graph, the reaction passes through a barrier, okay? And then, so how it passes through barrier is, you can see here, this is a rate determining step, means that is the slow step, how carbocation is formed. Once the carbocation is formed like this, it reacts with carbocation intermediate by mixing with water. And then finally, proton removal, then we get ROH. Okay, so this is mechanism, or even simpler is nucleophile when attacks with tertiary butyl compounds. You see, at this stage, you form a carbocation. This carbocation will react with nucleophile to get the product. So this is the fast part, or the quick reaction. This is the slow step, because you require some input of energy to form a carbocation. Now, let us see, we have looked at solvent, we have looked at polarity and so on. Now, let's look at the effect of leaving group. So, simple thing, SN1 reaction will be, depending on the leaving group, it speeds up. So we are having very good leaving groups like tosylate, okay, and ammonia, or very good leaving groups like iodine, water, bromo, and very poor leaving groups like hydroxyl or amine groups. If these groups are attached to the group what you are to leave, it is very hard to leave, despite you have a very strong force. So which means you are breaking the leaving group bond, which is faster, and then attack of carbocation with that nucleophile. Then you get the final reaction, which is under completion. So this is one important point which you should be remembering. Okay, and at the same time, the important take-home points for SN1 mechanism is how the ease with which the leaving group will dissociate, and the stability of carbocation. So always remember, stability of carbocation in polar solvents, it is very good. And if you have more substitution on the carbocation, more stabilities. So then it is easier to cleave. And nucleophile doesn't matter much. That is the reason it is SN1 during the rate of a reaction. And weaker base, when it is tightly bonded over carbon, and it is easier to break. So these are the important points, or the take-home points with respect to SN1 reaction mechanism. Now, let's see what happens if you see the effect of the concentration of the base also into the picture. So what happens is, in this case, you are taking a bromomethane, you add some base like nucleophile NaOH or like that, you get methanol. So here, if you increase the concentration of base, then the rate of the reaction quadruples. Means if both this and this are increased, the reaction rate becomes 4 times, which means there is a dependence of base with respect to substitution reactions, which gives rise to what is called as substitution nucleophilic bimolecular reaction. So bromoethane is converted into methanol, where the rate of a reaction is dependent on both substrate along with base. Okay, so even this is a very classical example which many of you might have already studied. Now let us see mechanism more deeply. So this one, for SN2 reaction mechanisms, Hughes and Ingold, they have proposed the following mechanisms where the hydroxyl group will attack. Okay, at the same time, the bromo will be there at transition state. Please observe everyone very carefully. We have carbon forming 5 bonds. The two intermediate, it's a transition state. This can leave, this can be there. So it is very intermediate or a very transition state, which upon bromo departure, you get corresponding alcohol. Okay. So again, when you are putting more and more concentration, what you are doing is you are making a lot of molecules to react, okay, by a lot of collisions, which essentially gives rise to, this is the mechanism. So I want you to, everyone to follow this mechanism. You see how methyl chloride reacts with, okay, so this is methyl chloride, this is chlorine group, and hydrogen backside, and you have carbon here. It reacts with hydrochloric acid. Okay, and sorry, this is like methyl chloride will react with hydroxide, OH minus, OH. When this comes, chloro group will leave and this will attack. And you see the bonds, hydrogens are coming this side, where earlier it has moved, inverted. Just observe. Now, let us take a reaction with ammonia and hydrochloric acid. This is hydrochloric acid, ammonia. If you see, there is no inversion in the configuration, whereas here you can see inversion. Okay, so which essentially says, again I would like to show you, please observe here, transition state, attacks, it will be there, then it will move. Okay, so please, like this, this is the transition state. So OH attack, bromo leaving, and that will be a transition state. Okay. So this is the mechanism of SN2, nucleophile, how it, especially how it is blocked in the front side and how it occurs in the back side. Okay. See now, this is a very important point. Nucleophile, since it already has electron rich, okay, it must attack the electrophile, whatever you are getting delta plus from back side as compared to that of leaving group. Okay, where front side it doesn't work, okay, because there is a blockage. You already have a halogen here. How it can come and attack again in electron rich molecule, repulsions will be there, whereas a halogen is here and the nucleophile is coming from other side, so one should leave, one can come and attack like this. Okay, so always front side attack is blocked when you have halogen, back side attack is, it will work out. You can see here. So the important point is the transition state, where you have 5 coordinated system, which is very unstable, which gives rise to inverted carbon. Okay, so that is what I told you. What you started from here, this gets inverted. You might have seen in the scheme how the animation. So because of backside attack, where you get inversion in the carbon. So due to which you get electrophilic carbon, and these things are in the same plane. Now let's look at the understanding of the mechanisms in this. So you are breaking the halogen bonds and forming the nucleophile bonds simultaneously. So what happens is you get a pentacoordinate system, carbon pentacoordinate, very unstable. So this, what happens is, in order to get the best overlap with the nucleophile and all, the leading group is being pushed with inversion along with retention of tetrahedral geometry. Okay, so like this. So you get a pentacoordinate and remove the halogen out, you get an inverted configuration. So this is a very important aspect which I think many of you might have already learned. Now, let's see, this is the inverted configuration. I think many of you are aware that it is an inverted umbrella sort of configurations, which like many of you might be uh, aware. Now, you can see here like how the intermediate it happens and how it stabilizes to give rise to this. And depending on the mechanisms of reaction rates, we can have, just hold on for a 1 minute. I would like to just give me 1 minute. There is some issue. Yeah, I'm sorry for the inconvenience. Okay, so there was some issue with the. Yeah. Okay, so I hope you can view the slide now. In this case, you can view here how SN2 reaction, which is exactly opposite or like reactivity wise, if you have bromo product, the reaction relative rate is very high. But if you start substituting it, more and more hydrogens replacement with groups, what happens is the reactivity rate reduces. When you go for tertiary butyl bromo compound, there is no reaction happening, which essentially says this follows SN2 reaction kinetics with respect to hydrogen's replacement. So these are the important points which you should be aware of by with respect to the stereo isomers and how is the reaction rate. Now, okay, so let's look at the reaction coordinate for even for this. So reaction halo compounds you are converting into alcohols. You can see you have a, the transition state pentavalent carbon, which is a activated or transition state slow step, and then after that it is a very quick step with respect to the product formation. Very important aspect, effect of substituents or the steric effects. And you also look at the amount of energy needed in order to have this kind of arrangement and bond breaking, bond attaching. So these are some important points with respect to the reaction coordinate and how much energy inputs need to be given. Okay. Let us look at different leaving groups. Okay. Now, you have iodo Yeah, I hope you can hear me now. Yeah, can you hear me?
Yes.
Okay, sorry for that. I think there is one more like power UPS off or something. So that was sorry for the trouble. Let me again. Okay, okay. I will try to. We have still 10 minutes. Okay, we'll try to. Okay, so I hope you can see the slide now. I'm using my computer now. Okay, so here you can see here, depending on different halo groups like iodo, bromo, chlorofluorine. I already told you compared to iodo group, fluorine is very least leaving group. So the reactivity rate wise, fluoro compound is very less as compared to iodo group. Same nucleophile attack with respect to different groups, we get the different reactivity. So in general, for halogen substitution, you have a stronger the base, the better will be the nucleophile. So this is very important aspect because iodine is a very good leaving group. OH attacks very fast. Okay, so please look at this one more example. Bromo is being left and iodo is being added to form in the reaction you are doing in methanol with respect to protic, aprotic solvents. If you have aprotic solvents, the reaction rate is 500 times faster because, especially methanol and acetone, if you have protic solvents like where you have hydrogen in OH or like that, they decrease the power of nucleophile. Nucleophile is here, and they form very strong hydrogen bonds with respect to solvent protons. That is the reason you don't have any such things in non-polar aprotic or, for example, aprotic solvents, due to which the reaction rate is enormous. Yeah. So these are some interesting points. And in using substitution reactions, especially SN2, we can make wide variety of molecules like alcohols, thiols, ether, amine, alkyne, and nitrile, like this. Whatever compound is there, use the nucleophile, replace, and accordingly you get. So this is the generalized schemes with respect to various alkyl halides. Let's conclude this substitution reactions, where SN1, SN2, you can simply compare and contrast by single step versus one step versus two-step mechanism, and rate determining step versus bimolecular, uni versus bimolecular. Both you can have, especially SN1, inverted configuration with respect to relative configuration along with retention. Or in SN2, it is more of inverted configuration. And this is the order of reactivity. Tertiary is greater than secondary in the case of SN1. In SN2, it is reverse. So this part, I think many of you are already aware of. Now, let us add some few points with respect to substitution reactions. Even many of you might have already studied Friedel-Crafts reaction, where haloalkenes, now whatever I have shown is aliphatic. Let us take haloarenes. They go to unusual electrophilic reactions like halogenation, nitration, sulfonation by Friedel-Crafts reaction. Again, you are looking at orthodirecting, para-directing with respect to how the substitution happens. By like also you understand orthodirecting, para-directing with respect to like resonance structures. Okay, different resonance structures, whether it is ortho or para positions, you can easily understand. Now, you can see here, you can halogenate chlorobenzene in presence of anhydrous aluminum, iron chloride, where you get para dichlorobenzene, and nitration also we can do for chlorobenzene, and sulfonation. Okay, same way we can add methyl group, a very very important reaction, Friedel-Crafts reaction, okay, where we can get a para group which is dominant. Okay. Same way we can also add acetyl chloride groups like this to form corresponding acetophenone complex molecules like this. Okay. So these are all electrophilic substitution. So that aspect we should also consider. And the last aspect before we close the substitution reactions is free radical reactions. We have free radical reactions where by means of addition. So now till now we have looked at substitution reactions, electrophilic and all, but now let us look at addition reactions by first free radical reaction. I think many of you are already aware of these reactions. You are adding a hydrogen halide to an unsaturated carbon. So you get hydrogen bromo being added. You can have peroxide initiators which will be cleaved. They form a halide radical. This is the active part. This active part will add, okay, to alkene, and you get an alkyl radical. This alkyl radical will react with hydrogen halide to give alkyl halide. So this is based on addition reactions. So we can also have addition reaction with respect to nucleophiles by simple strategy. Here I would like to show you three things before we end the class. Is how a new bond is formed between nucleophile and electrophile of C double bond. How you break the pi bond and then you form alkoxide. Okay. Then finally alcohol. Just I will show you one thing and then we can stop at this stage. You have a nucleophile and you have a carbonyl group. Okay, what happens? This all bonds will be directed towards oxygen and you get electron cloud. So you get delta minus and this is delta plus. So this nucleophile will form attacks here. And then after working them, you get corresponding alcohol. So this is nucleophilic addition under basic conditions. Especially anionic nucleophiles like this hydroxide group will form an alkoxide. This alkoxide, when it is you add some amount of small acidic part, you get a corresponding alcohols. Okay. You can use several nucleophiles like Grignard reagent, okay, and the butyl lithium and lithium aluminum hydride, sodium borohydride, and so on. So these are several examples of nucleophilic addition. In tomorrow's class, we shall look at weaker nucleophiles. Okay. At this stage, I mean, probably we can stop at this stage. And is there any doubts? Are there any doubts with respect to? Is there any doubt to anyone? Yes. If there are no doubts, we can take the attendance and then we can close. And also, just one announcement I would like to make for the tomorrow's exam. CLA 3 lab. Yeah. So I hope there is no doubt, right?
Yes, sir.
Okay. So if there are no doubts, and since most of these things you might have already studied, as soon as I upload the material, please look at the basic features about this, and then we can go ahead. Okay. So what we can do, we will stop the recording. Yeah. And